Hi, thanks for tuning in again. This is Jeff from JPL, and today we're going to talk about some of the ideas behind how we put things in space and why they stay there. So, as you might imagine, the answer has a lot to do with gravity. Now, one way to think about gravity is the old saying, what goes up must come down. And that is useful, but we really need to think a little bit more carefully about what we mean by up and down. So one way to think about this is down is the direction towards the most massive object around that's so massive that the mass of all the other things nearby doesn't matter. On the other hand, up is simply the direction opposite of down. So the next idea we need to talk about is the independence of horizontal and vertical motion. Now what that means is when you have an object moving horizontally and an object moving vertically, the motion in both directions is completely independent from one another. So that's a little hard to explain. So we'll start with an example. If this pen is a bullet, and if I fire a gun in this direction, then the bullet is going to move in this direction and fall as gravity pulls it down. Now, if I, at the same time, hold another bullet in my other hand, and if I drop it at the exact same time that I fire the gun, both bullets are going to hit the ground at the same time. Now, the bullet that I fired out of the gun is going to be a long way away, but they will hit the ground at the same time. And that's because when I fire the gun, I'm only giving the bullet horizontal motion, assuming I'm holding the gun horizontally. But that distinction between horizontal and vertical motion is really important for thinking about how things go into space and stay there. So now let's discuss how we actually throw things into outer space. So imagine you're standing on a baseball field and you throw a baseball as hard as you can. And you throw it up at some angle. So it goes up and over, and it'll hit the ground somewhere in front of you. Now, suppose you're standing on a building and you throw the ball at just the same strength, as hard as you can. It's going to hit the ground farther away from you than it would if you were standing on the ground. Now, suppose you're standing on a mountain that's really high up, and you throw the ball as hard as you can. It's going to hit the ground even farther. Now, as soon as we let go of the ball, the air in the way starts to slow it down. As you know, the air is made up of little tiny molecules that are distributed throughout space, including the path of the ball. So the ball slows down because it hits these air molecules, and eventually it'll hit the ground. The key to remember here is that the ball is moving horizontally and vertically at the same time at different rates throughout the path of the throw. So at this point, it's moving to the right and it's moving up because the ball was just thrown. At this point, it's moving right but slower, and now it's moving down until we finally get to here, and it's not moving to the right at all, and it's not moving down either because it's stopped. So what happens when you throw the ball from high enough that the ball never even hits the ground? Suppose we're standing on the planet and you have a very, very, very tall mountain up here, and you throw the ball. If you throw the ball hard enough, it will miss the ground completely and just stay in what we call an orbit around the planet. Now, in order to do this at the planet Earth, you have to throw this ball at about 17,500 miles per hour. But if you throw it at just the right direction from the ground instead of from a mountain, it will actually miss the ground forever. The reason it misses the ground forever and doesn't slow down in the horizontal direction is you've given it enough vertical motion this way to get it out of the atmosphere, which let's say is about this height, and enough horizontal motion to miss the ground completely. So we've just described how things get put in orbit and why they stay there. Now, there's another detail that was brought up recently by the record-setting freefall of Felix Baumgartner, the Austrian daredevil. Felix Baumgartner went up in a capsule attached to a balloon, a very, very large balloon. And once the balloon reached a certain height, he jumped out and he fell straight back down. Now, there's an important distinction here. When Felix went up in his balloon, he had vertical motion. He had zero horizontal motion. And that's why when he jumped out, he fell straight back down to the surface instead of going into orbit. When the space shuttle launches, it has vertical motion and horizontal motion. In fact, if you're standing at the launch site or near it, you can see that it's moving away from you up and over. And that's because it has to reach a very high speed going sideways in order to actually stay in orbit. We started this week talking about how what goes up must come down. As you've seen, a better way to say that might be what goes up must come down unless you push it sideways too. This week, we talked about how we put things in orbit around the Earth. Next week, we'll talk about how we take things from an orbit around the Earth and put them in an orbit around another planet. Thanks for watching, and don't forget to subscribe.